We are very pleased to have Peter Molnar as the invited speaker here today. He's sitting in the first row here, and I think there is no big need to introduce him at length. You probably know his name and his works. If not, I encourage you to visit the Wikipedia site, which describes his career and a couple of distinctions and medals he has received. What is not on Wikipedia is that he has a very busy schedule. He is traveling a lot, and so I'm very happy that you made time to come to Lausanne and give this invited presentation. The second thing which is not on Wikipedia is that Peter's grandfather and other ancestors came from Hungary, and so from his name you can say that somebody in that family had a mill. And if you think of mill, you can also think of Tibet in a sense. And today in presentation given by Peter, he will discuss the growth of the Tibetan Plateau.
Thank you, György. And György insists that that's the way you're supposed to pronounce his name, not György or any of that. György, something like that anyway. And thanks, and I didn't know I had a Wikipedia site. Is that right? Don't think about it. Okay, I'm going to talk about Tibet and in many simple ways. And let's just start with some elementary parts that you all know. Yeah, there we go. And then the pointer is this one. Yeah. Okay, so this is, of course, a map of Tibet. The red is Tibet. This is showing reconstructed positions of India at different times in the past. These 2 points, one in the northwest, one in the northeast, with an outline of the rigid part of India, ignoring everything to the north, going back at different times, at times of magnetic anomalies that are 10, 20, 30 million years ago or so. Whoops, I'm supposed to be in here. And plotted on this side is time, going backwards, of course, and distance from the present, the northwest corner, the northeast corner, moving quite rapidly in Cretaceous time before collision, more than 100 millimeters a year, and then collision sometime in around 40 or 50 million years ago, and an abrupt slowdown. I think most of you are aware of this. Advance now. What do I do? Nope, that's wrong. Oh, no, advance, right, no. And just a reminder, I think most of us believe today that southern Tibet was bounded by an Andean margin. This is a diagram that Lydia Steisch put together a couple of years ago, summarizing mostly other people's work. So a cross-section through the Andes, vertically exaggerated above sea level, what Tibet looked like before collision time. Tibet would then grow into a plateau that's roughly twice as wide as this. I think most people accept this image of what Tibet looked like before collision time. If you go outside of Lhasa just a little bit, this is a conclusion that's hard to avoid. Okay, now I'm going to show you an animation that Tanya Atwater put together, Tanya Atwater, a few years ago. India on the left, Asia on the right, water in between. The tan shows crust, thin crust under the ocean, of course. The darkened red is mantle lithosphere, then the lighter red is the asthenosphere. And I hope I can make this work. Probably, yeah, there we go. So I'm going to run it a couple of times. India slides, oh, there we go. All this modern technology is really hard for me. So let me get myself coordinated. That's the pointer, yeah. So I have to, when I practiced this talk, it wasn't going to take very long, but no, nope, that one. Well, I think you're not going to, what do I do to make this work? Nope, that didn't work. Here we go. So I'm going to try to make it work again. And what you would want to look at is India. First, you build the Himalayas, slices of India. The crust of Tibet thickens. And the feature that I'm going to really talk about is the speculative part of it, what happens underneath. So I can't keep up with this, but thickened the crust to build the Himalaya, thickened Tibetan crust, and ran it back already. Oh well, the hell with it. Just now to summarize where we are, Tibetan crust is thick. I think that's undeniable. And because of area isostasy, Tibet stands high. pretty simple. Crustal shortening thickened the crust. That's how you made the thick crust. Some thickening in southern Tibet occurred before collision. More, and perhaps most of the thickening occurred afterwards. I think the fraction that's occurred since then isn't clear. At least I don't think we know that yet. And I'm being rather careless in the word collision. For collision, when I'm talking, I mean when India met some subduction zone. I'm well aware of paleomagnetic evidence, which I think is reliable, showing that the shortening within Tibet was probably much less than we used to think. But I don't want to worry about that. Not today. Okay, so to start where I want to go, this is a map today where the blue symbols, the black symbols, and the red symbols show locations of earthquakes. These are lower hemisphere diagrams of the focal sphere. So the blue ones show normal faulting. You all know normal faulting. And the lower hemisphere, so for instance, that earthquake would show normal faulting slip on north-northeast trending planes, either dipping to the east or to the west. The black ones show strike slip. Let's take that one. That would be either right lateral on a northwest trending plane or left lateral on a northeast trending plane. And the red ones are showing thrust faulting. And what you see is normal faulting throughout Tibet at high elevation. Plotted down here, elevation coming across 5,000 meters. The normal faulting is virtually confined to high altitudes, one exception, flexure of the Indian plate out in here. And the thrust faulting and reverse faulting is on the flanks at lower elevation. This is undeniable, and there's plenty of geologic evidence now to corroborate it. The image that we take away from this is that Tibet is just a humongous piece of ripe camembert cheese. And I suppose since we're here, it should be a vacherin montor, which actually tastes better than a camembert. And it's spreading apart, spreading onto Southeast China and onto the Indian plate. This is the simple image we have of what's happening today. Now, I remind you, normal faulting cannot build a high plateau. The normal faulting that's occurring here requires some change in the development of the plateau. This is an inescapable fact, and from my point of view, this is the most important event in Tibet's history once you started building a plateau. Some change must have taken place. Now, I want to briefly digress here. Actually, normal faulting comes in two flavors. There's this north-south striking grabens with east-west extension. This is what I'm going to talk about, or what's going to be central to my talk. But let's not forget, we also have these east-west striking low-angle normal faults in southern Tibet, sometimes called South Tibetan Detachment System by others, not by me, but just so you know what we're talking about. And I bring this up because this was recognized just before the first Himalaya Karakorum Tibetan meeting, which was in '85, by Jean-Pierre Burg. This is a cross-section across the Tethys Himalaya, and he found a normal fault in here. And he wrote, the faulted contact has been interpreted as a thrust, which is not consistent with the northward shearing of the leucogranites which were underneath, and the normal faulting is suggested by the superposition of unmetamorphosed sediment on staurolite garnet schists. So what's reference 41? Well, let's look at reference 41. This is another paper also published in 1984 by Jean-Pierre. And here, I quote the whole abstract. Our study shows that the leucogranites suffered a northward shear deformation, and then he has gravity-driven décollement. Again, this is a cross-section further south, the main central thrust lying over here, Jam at the Tibet-Nepal border, Nyalam. And in here you can see this unmetamorphosed sedimentary rock. I have one quibble with this. Some of us spent 3 days in the Alps observing these magnificently, highly deformed rock, and we were, of course, enthralled by all this, and I really don't think those rocks were doing this in vain. I think, actually, they enjoyed it. So my contention is that deformed rocks do it. They don't suffer a bit. They do it with enthusiasm. Anyway, Jean-Pierre is gone and left us. He's retired. He's finished. But we ought to let him in. This is a really good wine. It's not a Swiss wine, I confess, but anyhow. Okay, let's get back to normal faulting as we see it today. So we have normal faulting, and I'm contending you don't build a high plateau with this. Camembert cheese doesn't get thick by being taken out of the box. It becomes thin when you take it out of the box. And a lot of very good work done, mostly in the 21st century, has gone into Tibet to date when these normal faults became active. So this is a map, you recognize Tibet in the middle, and sites where different people have gone in to date when normal faulting and east-west extension on those normal faults began. And not all of these dates are between 15 and 10 million years, but most are. So we have 10 to 8, 13, 14, 10 to 6, and so forth. There's a couple that might be younger, and a couple of very old studies, 1992, conceivable some of you weren't even born then. But the summary picture here is that this onset of east-west extension and crustal thinning by normal faulting dates from about 15 to 10 million years ago. Now we can look at this in another way with GPS. This is a plot with GPS points in Asia, Tibet, of course, in the middle, Tarim Basin, Tian Shan, relative to India. Usually these are plotted relative to Asia, but plotted relative to India. The green ones are ones that look aberrant, so don't pay attention. The white are just going so much faster than the red that if we use the same scale, this would just be obliterated. But what you see is there's an eastward component of motion on the eastern side relative to India, and on the western end of the Himalaya in western Tibet, there's a southwestward component. So clearly, divergence is occurring within Tibet. That's an inescapable conclusion, and that's the case all the way up into northern Tibet. I'll show you in a second another way of looking at this. But what one can do from this plot is calculate strain rates. So this is a map where it's been gridded. These are strain rates. The arrows, of course, the divergent arrows are showing you extension. The lines are showing you convergence. But the colors, the blue and the green, those are showing areal expansion. So there's no direction. This is how much the area grows. And if the area is growing, well, then the vertical has to be compressed or the crust has to be thinning. And the reddish colors, of course, are showing contraction. Well, in the Himalaya, there should be contraction, yellow up in here in the Nanshan. But what we can do is we can calculate strain rates for this whole region, and I'll come to that. But if we look at just northern Tibet, relative to one point in the middle, Shuanghu, you can see divergence. The points to the west move to the west, points to the east have a big eastward component. This whole area is extending. And as I said, we can calculate rates. Now, if you take those rates, those strain rates, areal extension converted into vertical equal, vertical contraction, assume the whole crust contracts, assume area isostasy, so extrapolating present-day strain rates to 10 to 15 million years, you predict a 1,000-meter drop in the height of Tibet. In other words, 10 or 15 million years ago, Tibet would have been even higher than it is today. Not an easy place to live probably then, but we weren't around to live, so it doesn't matter. It doesn't matter to us. Okay, so just a summary of where we are with this. Between 15 and 10 million years ago, Tibet crust stopped thickening. Actually, I should say we don't know when it stopped. We only know that it started to thin at this time. Began to spread apart. Crust thinned, grew outward to become a wider plateau, and the mean elevation began to decrease. So what happened physically? What was going on? And I'll give you my version. Of course, there must be plenty of these that differ. But if you imagine a crust overlying a mantle lithosphere and you shorten this horizontally, you thicken the crust, well, you make a mountain range because you have a crustal root. Area isostasy will give you a mountain range. But you have to do something with the mantle lithosphere. If we assume that the composition of the mantle lithosphere and the asthenosphere are the same, the mantle lithosphere is colder, so you push cold material down within warmer material. This is going to be dense. So this is going to be a load. It's like an anchor or a heavy keel on a ship. If you can remove that, it should be unstable. It's gravitationally unstable. You have high density next to low density. That's what makes an instability grow. So if you can remove that, and this light blue is showing you the removed material, you remove that, so you remove the dense mantle lithosphere. Don't have a word for it, so deblobbing. The surface should go up. You lighten the load. And when you do that, the whole region gains potential energy, available potential energy. A better way of looking at it, it's potential energy that can actually do some work. And that potential energy then can power outward growth. You have crustal thinning. The flanks of the range are going to undergo crustal shortening, so you're going to thicken the crust out on the flanks as the surface drops down again and you heat what's underneath. The hotter mantle in here then can lead to volcanism, either both by decompression melting of the asthenosphere and by heating the thinned mantle lithosphere. So how does one test this? Call this a hypothesis. What does this predict? Removal of mantle lithosphere, what does it predict? Well, it predicts marked lateral variations in density and therefore seismic wave speeds in the mantle, because if you have blobs sinking into the asthenosphere, they should have different wave speeds, should be different densities. Enhanced volcanism, when you thin this region, you heat the mantle lithosphere, you also have decompression, you may have decompression melting in the asthenosphere. You should have crustal thinning beneath the plateau. Well, that's where we started. Outward growth of the range, or the plateau, because as you collapse, you have to accommodate this material, so you have thrust faulting on the flanks. And then you should have an increase in surface elevation when you drop the blob off, and then followed by a decrease, followed by subsidence as you extend this whole region. So let's go through these predictions, starting with lateral variations in mantle structure. So this is PN speeds. PN is the P wave that travels just below the moho in the mantle. This is an older study by these folks. I put it in because they were the first to really show this. There's been many improvements. This is well known. It's color-coded so that the warmer colors are lower speeds than 8.1, cooler colors, higher speeds. 8.1 is an arbitrary decision here. Don't forget that the base of the crust, the uppermost mantle under Tibet, is much higher pressure than under lower areas, and that increased wave speed. So 8.1 is a little fast for many parts of the world to be called warm, but I'm going to say it's warm if it's lower speed than that. It's cool if it's higher speed. And you see this warm area in northern Tibet, this lower speed. This yellow line is showing you where SN, the S wave traveling in the uppermost mantle, is very highly attenuated. And high attenuation, again, suggests high temperature. So this is suggesting high temperature in the north, lower temperature in the south. Now, here's another study. This is a study using a profile through Tibet over in here, sketched in with that line. And what they've used are S waves, but also multiple reflections of S waves. So imagine the surface is up here, the moho down here, an S wave comes in. Of course, the S wave converts to another S wave before it reaches the station. The S wave can come up and convert and make a P wave. The P wave travels faster, so the P wave would actually arrive, this little S, this S little p, would arrive slightly before this direct S wave. But you can also get an S wave that will come in, reflect off the surface as a P wave, come down to the moho and reflect back as a P wave. And if you're in the right distance range, which is relatively close but not too close, this reflection off the moho is very strong. It's almost a converted, entirely converted phase. So you can get a strong signal there. So the next slide is going to show you seismograms to illustrate this. This is now a profile, Lhasa terrain in the south, Changtang further north. So a profile going up across here, B down here. Time on the seismograms, each of these is a seismogram. Time increasing downward. They're all aligned at the time of the S wave. This is the direct S wave coming in here. And this phase that you see that's strong is this multiple reflection that's coming in this way. And obviously, the time difference between the direct S and this multiple will depend on the thickness of the crust. The thicker the crust, the longer the delay, because this phase has to pass through more crust than that one does. And what you can see, this is the red is showing the initiation of that phase, the onset of that phase. And you can see it's the time interval between the direct S and that phase is greater in southern Tibet than in northern Tibet. Converted into depth, crustal thicknesses would be 75 kilometers or so down in here, getting as thin as 60 over in here. Now, this is a very simple way of looking at this. I like this because you don't have to be a seismologist to look at this and understand it. This is really clear. The next is a bit more complicated. These are what are called receiver functions that have been collated to give you an image from John Novalek and his colleagues. The previous set looked across just this part in here. It didn't include the Himalaya down in this area. So this is a plot. The red is showing you the depth where you convert from a high speed below to a lower speed above. So that's the MOHO, of course. And then you have this double layer in here. I'll come back to that in a second. And then coming across in here. If you draw a line through about 60 kilometers, that black line comes across. And this area in here, this is the thicker crust that you have in the south than the north. Now, these authors looked at this in more detail and in subsequent papers, and they concluded that this double thickness layer is actually eclogite. Down in here, I guess in this continent you're supposed to say eclogite, but I don't know how to do that. This is a layer of relatively dense material, but still crustal material. So the point that I'm trying to make here with this is you have similar elevations in southern and northern Tibet, but you've got thinner crust in the north, and you have this eclogitic basal layer in the south. This calls for a hotter upper mantle in the north than in the south. And I would argue that I'm showing you only a fraction. I could spend an hour on just data that show this, but I don't think you want me to do that anyway. So what's the next step? One can use seismic topography, popular technique, and start with one of the first of these studies, Tillman Nee and their colleagues. And they had a line of stations. This is not the same line of stations that the previous authors used. This is further east. A line of stations going across here. This is their tomogram, drawn, of course, at a 1-to-1 scale. So coming down to 500 kilometers, this is the part they have confidence in. You clearly see streaking due to where the rays came. So there's imperfection in this. If you put this in the context of the whole of Tibet, main central thrust, the main boundary fault out in here, coming across the suture zone would be in here. They're saying that this high-speed zone is a blob or a piece of lithosphere. They're drawing it possibly as continuous. They have this hot region to the north, but this is just, they don't have evidence for that. Their tomogram lies in here. Now, if you put this in a bigger scale, this picture, this would be this region in a north-south profile. So south over here, this is the Indus Sangpo suture, the Bangung Nujang suture up in here. And this high-speed region, you see it stops at about 300, a little greater than 300 kilometers depth. So these data were then used in a global study by Lee, van der Hilst, Meltzer, and Engdahl. The same data were put into a global study, and this image came out as a profile. And I call attention to this because this profile, notice, first of all, here's the Indus suture. Indus suture is way back here, hence it's way off to the side there. Here's the Bangung Nujang suture. In the Tillman Nee paper, the high-speed zone is right under that. In this case, it's quite far to the south. But more importantly, these folks have it going from 100 to 300 and 330 kilometers. These folks have it going from 300 kilometers to more like 500. It's the same feature manifested in the data. It's just a different way of looking at this. You know, what do you do? I'll make it worse. So another tomographic study by Ren and Shen, where are they? Ren and Shen, they're looking down in southeastern Tibet. They had a network of seismograph stations in this area. I've drawn this block where their study, Ren and Shen's study, is relative to the previous studies. P waves on the left, S waves on the right. P waves from minus 1.5 kilometers % speed anomaly to plus 1.5 S, twice that, minus 3 to plus 3. if you compare these 75-kilometer depth, you know, the red blobs are pretty much in the same place, going down to different depths. Profiles, there's one profile they've drawn across here, AA prime, doesn't show much. But what this is rather splotchy. And I contend there are two ways of interpreting this. One is to say that it's noise, which is a polite way of saying, I won't say what the impolite way is. The other is it's blobs. The blue are little blobs, little drips, so you paint the ceiling and drips fall down and you get these blue regions, high-speed regions, and then something has to thin in between and you get the red regions. You'll notice that the high-speed region that Tillman, Nee, and colleagues had doesn't show up clearly here, nor would it in the Lee and Vanderhilst further east. Okay, one more of these. This is by Chen, Nyo, Trump, and their colleagues, and I emphasize in the title, lithospheric foundering. That tells you what they think. Map of Tibet. So 80 kilometers, this is this low-speed region in northern Tibet that I showed you with PN. Higher speed, not very high, in southern Tibet. 175 kilometers, high speed in southern Tibet. Lower, not terribly low speed. This is percent over here, minus 3% to plus 3%. And I think these are S-wave speeds. I confess I've forgotten. And then going deeper with at 350 kilometers, just a cylinder of high-speed material. The next slide is going to show a profile coming across southern Tibet in here. The feature that you're supposed to see is the thing outlined in blue right there. So here's this profile, east-west profile, high-speed region going down. This is plotted as speed anomalies, percent anomalies. This is the actual speed. So there's a high-speed layer down here centered at 150 kilometers from what they've done with a lower speed above. So what do we get from tomography beneath Tibet? Well, there's an expression in English, pay your money, take your choice. If you have a idea you like, I'm sure you can find it within this. I would argue that we have two criteria for deciding what we believe in tomography. One is we trust the authors, but we can't publish that. We certainly can't publish it when we don't trust the authors. And the other is it fits what we already believe, which makes it hard to learn from. But I'm sure whatever you think you can find here and here. I might retranslate that last thing. If seismic tomography is seismology's emperor, then who is the tailor? I'm referring here to Hans Christian Andersen's story about the emperor and his new clothes. Okay, let's move on. Enhanced volcanism. I would argue that there's no question there's lateral variations in seismic wave speeds, though I don't think we have a very good image beyond northern Tibet being low speed and southern Tibet being higher speed. Whether it's high or just higher, we don't know. So here's a map compiled by Ding Lin of volcanism in Tibet, colored so that the yellow are the younger ones, and they're all pretty much all across the north in here. They get back to 17 million years, but most are younger than roughly 10 or 15 million years. The red are somewhat older in many cases, but not entirely. This is really colored by geography more than anything. These are all potassium-rich volcanic rocks, and you have some of them even in southern Tibet down in here. And if you drive across northern Tibet, you see volcanic rock just about everywhere. This is basalt capping a ridge, a little bit of it dripping down in here. It's just about everywhere, but it's not voluminous. It's a thin layer, but you find this just about everywhere up there. And how do we understand this? Well, the composition of these volcanic rocks is special. On a plot of epsilon neodymium versus strontium 8786, crust's way out here because crust has lots of rubidium 87, which decays to strontium 87, so old crust will have a high value in here compared to mid-ocean ridge basalts where you're just bringing this out. And neodymium works the opposite way. Well, the Tibetan rock is in between, approximately halfway in between old crust, though the Tibetan rock is not crust, it's melted mantle, and mid-ocean ridge basalt. And the samples that Turner and his colleagues took are from way up here in northern Tibet. Well, how do they understand it? they understand it. Potassium-rich melt seeps into the mantle lithosphere. Potassium is an incompatible element, as is rubidium, which gives rise to strontium-87. So they seep into the mantle. They don't bring much heat, but they seep in. They pollute the mantle lithosphere as time evolves. They come in at the bottom of the mantle lithosphere. So you have a crust. This is a profile looking down. So the bottom of the mantle lithosphere would be someplace down in here. Thicken that region so you stretch the whole lithospheric column. And then if you remove the mantle lithosphere, you heat the bottom of the mantle, the remaining bottom of the mantle lithosphere, which is full of all of this potassium and strontium-87 and other incompatible elements, rubidium, of course. And that's what erupts at the surface. So I would argue that enhanced volcanism, that's certainly present in northern Tibet. I would not defend this as providing a simple view of what's going on beyond that statement. Crustal thinning, well, we talked about that. That's this, that's normal faulting within Tibet and the outward growth of the piece of camembert cheese, or vacherin Mont d'Or. I want to digress a little bit with this because this applies not just to the upper crust, but to the uppermost mantle. This is an old plot showing fault plane solutions of earthquakes. Again, these are lower hemisphere diagrams. That was showing normal faulting with east-west extension, this having a big either right lateral strike slip or left lateral on that plane. These two earthquakes occurred quite deep, 85 to 90 kilometers, almost surely in the mantle. And subsequently, a lot more work has been done on this. So now this is a plot looking just at this lower part of Tibet in here. This is work of Tom de la Torre and colleagues. This color-coded by depth, so the red ones are shallow. So for right now, I don't pay attention. The blue ones are the deeper ones, 60 to 100 kilometers. The fault plane solutions, again, are showing you essentially east-west extension all through here. And these are probably in the mantle, almost surely in the mantle, underneath Tibet, and lots of them. So this is not a rare phenomenon. And if one draws a cross-section through here on this red line in here, the blue ones down here, now these are back hemispheres. So these are showing you extension out of the page. You're stretching in and out of the page in here, down in here, and most of these are surely in the mantle. So the point is that the deformation of the crust is similar to that of the mantle. One can't say, oh, well, the mantle and the crust are behaving completely differently. At least in this part of Tibet, they seem to behave similarly. Okay, what about outward growth of the range? So this is a plot showing you a compilation, which I haven't updated recently, a compilation of places where there's been a change in the last, well, would be 20 million years if there were cases, but not going back that far. A change of some kind. Most of these, of course, are inferred from thermochronology or from sedimentation. They're not direct measurements of tectonic activity. But the point is that all around Tibet, all surrounding Tibet, there are indications that crust thickened at that time. And to start with one, let's look at the Tian Shan up in here, which is a good example outside of Tibet. The Tian Shan is roughly 200 kilometers, 250 kilometers down here, 200 kilometers wide. Geologic estimates would say there's at least 50 kilometers of shortening. These are lower bounds. It's probably not more than 200. If you doubled the thickness of the crust across the whole region, you'd get about 200 kilometers of shortening. The GPS shows you today that you're shortening across the western Tian Shan at 20 millimeters a year. This is fast. More than half of India's convergence with Eurasia is absorbed in the Tian Shan today. The Himalaya is still shortening rapidly, but out at this longitude, it's northeast-southwest. But the direct north-south component of India, more than half is absorbed here. So if you take less than 200, divide it by 20 millimeters a year, or 20 kilometers per million years, this would suggest that the whole region is younger than 10 million years. I'm not saying it's younger than 10 million years. There definitely was high enough terrain to erode here back 25 million years ago. But this argument would say that Tian Shan mostly is very young, much younger than roughly 10 million years. Take another one up here in the northeast corner. This is now going to be thermochron, work by Zhang Duan and colleagues. A cross-section through here. This is this would be south-southwest, north-northeast over here. Paleozoic granite thrust on top of Cenozoic sedimentary rock, and then they took samples through here to date using uranium, thorium, helium. And the dates show, this is age now going back from 20 to 200 million years, slow cooling until very abrupt cooling beginning around 9 million years ago. So they're arguing that rapid cooling 9 million years ago, this is when the thrust faulting on that fault began. One more like this from the Yopanshan over here, way out to the east of Tibet, next to the Ordos Plateau out in here. This is a very simple structure, mountain range across here with a cross section, basically one thrust fault. Cretaceous and older rock thrust on top of E is Paleogene, thrust on top of Paleogene rock, and they sampled this for fission tracks. Over here is age. The red is the age of the sediment, so this is all Cretaceous in here until you get to the younger Paleogene sediment. The blue are the fission track ages. Up in here, this is sediment that is eroded Cretaceous rock, so that's why the fission track ages are Cretaceous. But then these have all been reheated through burial and then suddenly cooled, again, very abrupt cooling here at about 8 million years ago. So the interpretation is that this big thrust fault became active 8 million years ago. And one last one, which is more complicated than the others. This is beautiful work by Alison Duval looking in here. What she and her colleagues did was sampled modern sediment, just went out to the river, took sediment in a series of drainage basins. These are a bunch of different drainage basins in here. And I'll show you one example from the upper Mekong. I've taken this and turned it on its side. This is the elevation distribution within the basin. So the highest region within the basin is about 5.5 kilometers. The sampling point would be at 3.8 kilometers, but most of the terrain is in this intermediate range between 4.5 and 5 kilometers. And they have fission track ages going back to more than 200 million years, and then up to the present. And they have apatite uranium thorium ages that go back to 80 million years with a big peak back in here. Now, if you have older fission tracks and older apatite uranium, you have to cool slowly. If you cooled rapidly and exhumed a whole lot of rock, these would all be gone. They wouldn't be there if you cooled recently, rapidly. To have these younger ones, you have to exhume rapidly and recently. Otherwise, that rock would still be buried. So if you take those data now turned back on its side the way it should be, and look at cooling at a steady rate, suppose you're just exhuming the rock off Tibet. Today, the 70-degree isotherm would be at about 3 kilometers depth. Tibet is at about 5, so this would be down, what, 1.5 kilometers or so. And the 110 would be at sea level. And if you had that cooling, you can predict the ages, the population ages of these detritus that you've gotten in your stream. So this is now a cumulative probability. This is adding up these as you go along. This starts at 100 million years back here. So already 20% of your ages, 20% are older than that. By the time you get to 80, you add a few more. And these are the data they get with the cumulative probability. The same with the uranium, thorium, helium in here with this rapid cooling at a later time shown over here. And the shaded areas are the fits. And the fits are no good, right? This is way above the line in here. This is saying that you cooled too fast, so everything should be older than it is. And this is showing that you cooled too fast for this little bit, but you did all right in here. This is a bad fit. One of my concerns with modern science is that as everybody wants to publish in tabloid journals, which only want the propaganda, they don't want the good science, bad fits get left out. You learn a lot more from bad fits than you do from good fits. So, moving on, of course, then they have to publish a good fit. If you have a slow cooling for a period and then abrupt cooling, you'll get a different population. The slow cooling, you need that to explain the old ones. The rapid cooling, you need to explain the young ones. And indeed, the cumulative probabilities then match quite well. So they did this with 7 or 8 different basins. This is now a profile from south to north. the Yarlingsangpo way down here, going across, and this is the age when the rate changed, when you suddenly got an increased rate of cooling, presumably, therefore, an increased rate of erosion. And those ages are mostly in the range of 5 to 10 million years in here, sometimes a big uncertainty. In one case, 2 periods of rapid cooling. But most of this is in the last 5 to 10 million years. And the simple interpretation, you can't appeal to climate in an easy way. The simple interpretation is the region tilted up at that time. So what about it? So I would say outward growth of the plateau occurring around 10 million years. That's consistent. What about increase in surface elevations? Well, this is a bit more problematic. I'm going to show you just one study again, Dinglin. And this is a bit complicated. You have a map of Tibet in here. Don't worry about these lines in here. You have samples that are within the Himalayan region, down in this area, and they're suggesting, and most of this is paleobotany, or oxygen isotopes or hydrogen isotopes. You have low elevations way back before the collision within the Himalaya and an abrupt increase here. That's not what I want to focus on. I want to focus on just a part of this blue line. The Linzhou is this site, Lumpala, Nima, they're up in here. I don't trust these myself, so that's not what I'm after. It's the Namling site in here. Namling is this site right in here where both isotopes and paleobotany have been used, and they get an elevation up here, paleo elevation of the order of 5.5 to maybe even 6 kilometers. And the point here is that you've had a big drop since that time. So there's the drop in elevation seems to be there. If you go back to the question, has there been an increase in surface elevation followed by subsidence? I think the answer is maybe not. Or maybe, but maybe not. The difference between maybe not and maybe is 0. But I don't think the tests are convincing yet. I continue to have a hope that we'll be able to do this at some point. So, to summarize, Tibet is high mostly, but not entirely, because it has thickened crust. Northern Tibet has a hot upper mantle. A major change occurred 15 to 10 million years ago. North-south shortening changed. We don't know when that stopped yet, probably before 10 to 15 million years ago. But the east-west extension began at that time. The idea that mantle lithosphere was removed passes most tests that can be put to it, and a hot upper mantle contributes to the present-day high elevation. To me, the big question is, how was mantle lithosphere removed? In one downwelling sheet in southern Tibet, which some studies would support, lots of little drips. You paint the ceiling, drips come down everywhere. That seems possible. Delamination, as Peter Bird imagined it, you peel it away somehow, or some other way. I don't think we know, but to me, this is the big unanswered question. Thank you.